Hello and welcome to today's webinar, How to Make Reliable Temperature Predictions, Battery Pack and Electric Motor Applications in CONVERGE CFD, brought to you by Convergent Science. Thank you for joining us today for this new installment of our webinar series. My name is Scott Davis, and I'm a part of the business development team here at Convergent Science. I'll be your host for today's event. We're excited to showcase Converge and its capabilities in battery pack and electric motor simulation. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Our speakers today are Dr. Tamara Gammaidoni and Dr. Jacopo Zembi. Dr. Gammaidoni has a master's degree in mechanical engineering from the University of Perugia, Italy, presenting her thesis on the CFD analysis of the cooling system of an electric motor. She recently participated and won the first Convergent Science academic competition with her presentation of battery pack simulation. Dr. Zembi is a postdoctorate researcher at the University of Perugia. His research focuses on CFD simulation for internal combustion engines with innovative fuels as well as sprays and innovative ignition systems. In addition to this, his studies have led him to use Converge for e-mobility applications, carrying out thermal analysis for batteries, e-motors, and power electronics. We thank them for joining us today, and the time is now yours.
Hi everyone, I'm Tamara Gammaidoni and my colleague is Dr. Jacopo Zembi from the Department of Engineering at the University of Perugia. Thank you for joining us for today's webinar. We will talk about how to make reliable temperature predictions, battery pack and electric motor applications in CONVERGE. Let's see a brief overview. We'll show two cases, a battery pack and an electric motor. And for both of them, we'll give you the motivation and goals to study these problems. We'll give you a brief geometry presentation, and we'll show you how we made the case setup in CONVERGE. In particular, we would like to enhance which aspects led us to achieve the best results. After showing the results, we will give you an idea of the applications and of the kind of evaluation that you can make using CONVERGE. Finally, we'll draw the conclusion, and we would like to enhance which parameters affect the simulation the most. Let's start with the battery pack case, which led me to achieve the first result in the 2022 CONVERGE academic competition. The motivation to study this problem is that the automotive industry is rapidly evolving and much of the focus is on electric vehicles. So in this field, a major problem is designing an efficient cooling system for the battery pack, in order to keep the temperature on the surface of battery cells within a certain range. It is fundamental to guarantee the best performance and to not exceed the safe operating condition. So the main goals are identifying the key heat transfer phenomena inside an air-cooled battery pack with ventilation holes. Secondly, to predict accurately the temperature distribution on the battery surface, while saving computational time. In the video, you can see a brief presentation of the geometry. The battery pack contains 24 lithium batteries connected by copper bus bars. And you can also find two holding plates which hold the batteries, and they are provided with venting holes. There is also an intake plenum with an inflow for the fresh air, an exhaust plenum for the warm air, and side walls which complete the box of the battery pack. Now I would like to show you how I made the case setup in CONVERGE. But first of all, I have to say that the battery pack geometry, the material properties, and the thermal data used as inputs derive from the experiments carried out at the University of Singapore. I divided the geometry in 6 regions to distinguish box, intake plenum, exhaust plenum, solid batteries, copper bus bars, and the holding plates. And you can find 2 streams, one for the solid region and one for the fluid region. One of the most important aspects to consider is that you need to use the conjugate heat transfer modeling. It is when heat transfer occurs simultaneously within and between fluid and solid regions. As you know, the predominant mode of heat transfer in fluids is convection, while in solids is conduction. And CONVERGE allows you to calculate the heat transfer both in fluid and solid region. But to complete the setup for a 3D CHT, you must first of all define the solid and fluid materials, then assign the appropriate regions to solid and fluid streams, and set up the interface boundary at which the CHT coupling occurs. An interface boundary consists of a single layer of triangles, but has 2 unique sets of boundary conditions, one for each side of the interface. In the figure, you can see the normals of the triangles on a battery. The direction of the normals is very important because they distinguish the solid region to the fluid region. And as I said before, the CHT allows you to calculate the heat transfer between a fluid region and a solid region. In particular, CONVERGE imposes thermal continuity across the interface, imposing the equality between temperature and heat fluxes between the fluid and solid regions. One of the major problems in the CHT is that the time scale for conduction is different and longer than the time scale for convection. So it results in a longer computational time. But CONVERGE provides the supercycle modeling that allows to save computational time, because in this method the fluid solver working on convection problem is paused for a small time period, allowing the solid state conduction solution to accelerate towards steady state. So in this way, it significantly reduces the number of cycles and simulation time. Using the supercycle modeling, the simulation requires 12 hours on 20 cores to reach the steady state after 15,000 iterations. I also gave you the CFL setup just to show which CFL numbers are used in the simulation. Now I would like to give you a brief overview of the boundary conditions. You can find 3 interface boundaries: the batteries, the holding plates, and the copper bus bars. One inflow where the flow rate is imposed, one outflow where the pressure is imposed, and the intake and exhaust plenum and external walls are wall-type boundary conditions. Here you can find the first important results regarding the boundary conditions of the external walls. In the graph, you can see a comparison between the convection, the adiabatic walls, and the law of wall with temperature of the wall assigned. As you can see, the results are particularly influenced by the temperature boundary conditions of the walls. Finally, in this project, the convection boundary is employed because it is more realistic than the adiabatic one and more conservative than the law of wall with temperature of the wall assigned. Regarding the physical models, I would say that it is a steady state simulation. I used a standard K-epsilon turbulence model because it is one of the most used in this kind of application, and it is also less computationally expensive than other turbulence models. And one of the most important aspects regards the near wall treatment. In fact, I imposed the enhanced wall treatment because a preliminary study showed wall plus values too low to use the standard wall function, as you can see in the graph. In fact, I want to remind you that the turbulent boundary layer has an inner region that can be divided in 3 sublayers. The viscous sublayers, also known as linear region, for Y plus between 0 and 5. The buffer sublayer for Y plus between 5 and 30. And the fully turbulent sublayer for Y plus between 30 and 400, also known as logarithmic region. The problem is that the grid density required to resolve the viscous sublayer may be prohibitively expensive. So CONVERGE can model the under-resolved viscous sublayer using one of several wall treatments for the turbulent dissipation rate. One of these wall treatments is the standard wall treatment that makes use of the law of the wall assumption for velocity in the log low region of a turbulent boundary layer. It is really important to notice that the standard wall function assumes that the cell adjacent to a wall lies in the log low region of the boundary layer, but as I said before, it is possible just for Y plus over 30. So another type of wall treatment is the enhanced wall treatment. In this case, it's a two-layer approach that blends a modified law of the wall for the log layer with an expression for the viscous sublayer. In this case, the resulting wall function is insensitive to near wall grid spacing, so the first cell can be in the subviscous sublayer or in the log region, and it doesn't make important errors. It also accounts for pressure gradient, heat transfer, and compressibility effects in the momentum equation. So on one end, this type of wall treatment results in a greater computational expense. On the other hand, it is appropriate for any Y plus smaller than several hundred, and it performs better than other wall treatments, in particular when near wall pressure gradients and heat transfer are important. So, as I said before, a preliminary study showed Y plus values too low to use the standard wall function. You can see in the video that the Y plus is around 5 on the surface of the batteries. For this reason, the enhanced wall treatment is adopted. And you can also notice from the graph that using a standard wall function would result in an underestimation of the cell's average temperature. Another very important aspect is the source modeling. I used 24 sources of type energy per unit time imposed as cylindrical shape inside the batteries because it is one of the most realistic way to model this type of sources. About the grid control, I can say that I used a cubic grid with fixed embeddings around the batteries and the bus bars, as you can see in the video and in the figures. I also used AMR to capture strong temperature gradients and the grid scaling to accelerate the calculation. In this way, the model reaches 3 million cells. From this graph, you can see that the grid size adopted is adequate, since a final one led to similar results for the Y plus. A simulation using also LED mesh was conducted, as you can see in the figures, but its results didn't match those of reference, and you can notice it from the graph. Therefore, fixed embedding is adopted. Finally, these are the results. From the graph, you can see the comparison between the numerical data that I obtained from my simulation and the experimental data provided by the University of Singapore. And you can notice that the local temperature on battery surface match fairly well with the results of the University of Singapore. Therefore, the model can be considered validated and predictive. Now, I want to give you an idea of the applications and of kind of evaluations that you can make using CONVERGE. For example, you can evaluate the temperature distribution on the battery's surface, as you can see in the video. And it is really important to find the hottest points on the surface of the battery or on the copper bus bars, or on the holding place, or on other parts of the battery pack. And you can also investigate how the flow field and the temperature field changes with different flow rates. Now, to conclude, we can say that CONVERGE made possible achieving reliable results thanks to the CFD modeling, the supercycling modeling, the enhanced Wall treatment in the turbulence modeling, the source modeling, and also the AMR and fixed embedings. So finally, the parameters which affect this type of simulation the most are the type of Wall treatment, the boundary conditions of the external walls, and also an adequate use of the grid. Thank you for the attention. Now I will talk my colleague Dr. Zembi, who will show you an electric motor case which we studied for my master thesis. Thank you.
Thank you, Tamara. So the second part of the webinar is focused on the thermal management of an electric motor. The cooling system is fundamental in this type of application in order to increase and optimize the motor performance and to keep the motor safe. In particular, the objective of this activity are predict accurately the temperature distribution and the flow field, optimize the cooling system, and save computational time for the CFD simulation. The electric motor is developed by Loccioni company, that is a partner of our university placed in the center of Italy. The company designs and builds test benches, electric motors, and other components for the automotive industry. And I would like to thank Loccioni company for the opportunity to collaborate for the master thesis of Tamara, and also the opportunity to share results of this activity. The geometry of the electric motor, boundary conditions, initial conditions, and experimental data are provided by Loccioni. It is an interior permanent magnet motor designed for testing electric motors in high speed and high power applications. The cooling strategy of the electric motor is twofold in this case. So the liquid cooling system is represented by an house water jacket in the outer shell of the stator. The air cooling system is an open fan cool type, so the air comes continuously from the outside, passes inside the engine, and finally it is extracted from it. To do this, two identical fans are used, one for the inlet and one for the outlet. And at the end of the presentation, we will see that the CFD model was able, in this case, to estimate the distribution of the thermal load dissipated between these two types of cooling systems. The main heat source of an high-speed motor consists of two parts, one inside the motor and one in the bearings. In particular, during the rotation, due to motor losses and bearing friction, a large amount of heat is generated. There are four main contributions for heat sources calculation. The friction losses caused by the friction between the rotor and the air, calculated as a function of the gas density, the rotor dimensions, and the angular velocity. Then we have also electrical losses, also known as Joule losses, that occur in the windings. Magnetic losses that include hysteresis and eddy current losses. And last, friction dissipation between bearing components relative to viscosity of the lubricant and contact between rotating bodies. First, I'd like to show you the geometry of the motor in CONVERGE, seen from outside, to highlight the external fundamental components. You can see the rear head, ventilation vents, the airflow, the front head, the outflow, and the external part of the stator. In the center part of the slide, there is a detail of the water jacket, and on the right-hand side, the conveyor to seat vents and the duct to direct the airflow and a picture of the heads. The internal part of the geometry is represented here in the slide. In the left-hand side, it is possible to identify the air gap, magnets, the stator, the rotor, and the stator slot for conductors. On the right-hand side, a schematic of bearings that are modeled, in that case, as a unique cylindrical solid body without sphere. This is a strong assumption, of course, but we did it to not complicate the model. So the case setup in CONVERGE is very complicated, since there are 3 different streams, in particular air, solved as compressible ideal gas, water, and solid. We selected 4 different materials for the solid parts in order to reproduce their properties basically in the best possible way. Therefore, the domain is composed by 21 regions and 65 boundaries. Boundaries are divided as shown in the slide: 1 air inflow and 2 air outflows, 1 liquid inflow and 1 liquid outflow, 51 interface boundary, and 9 wall type boundaries. After a literature review, we can state that we have not found such a complex and detailed CFD model. A consideration needs to be added for rotating bodies. We decided to set the surface movement as fixed to avoid rotating the triangulated surfaces in the model in order to prevent intersections between surfaces and the use of ceilings method. At the same time, the wall motion type was set as rotating, of course, in order to allow the simulation to take into account the rotating movement of the rotors and bearings, and in particular their effect on the surrounding fluid. This assumption was possible just for surfaces of revolution bodies, so the geometry was preliminarily adapted to this scope. This approach was simple to use and was a great alternative to the multiple reference frame technique. In the figure on the right-hand side, the fluid rotates around the rotor in the air gap with an helical motion type. The presence of resin into the stator slots, around magnets, and around the copper coils, as shown in figure, prevents heat dissipation and imposes a thermal limit related to heat glass transition temperature. This aspect is not negligible, and we have taken into account modeling the resin around these components using the contact resistance technique. For the grid parameters, after several preliminary tests, it was decided to use a grid base size of 6 mm in X and Y and 12 mm in Z along the motor axis. The mesh is built without using the HMR technique. We prefer to use fixed bendings around the most important components, such as ventilation vents, for example, bearings in the liquid circuit and in the air gap. Since it is a steady-state simulation, grid scaling technique is also used to accelerate the computational time, and at the end, the model reaches 3.8 million cells. Let me spend a few words on the comparison between experimental and numerical results. In that case, in our case setup, monitor points are used for saving temperature data. And basically, they are located where the thermocouples are positioned in the real motor to directly compare numerical and experimental temperatures. To summarize the physical models and numerical methods, as I said before, it is a steady-state simulation. We use CHT modeling, the supercycling methods previously described by Tamara. The turbulence is solved using the standard K-epsilon model that is the most commonly used for this type of application. And now it is important to focus the attention on 2 different aspects that have been crucial to obtain good results. That are the energy solver and the source modeling. CONVERGE can solve the energy equation using total or internal energy approaches. The total energy solver is recommended in simulating high-speed flows that include discontinuities to enforce the energy conservation. This choice has been fundamental for us to obtain predictive results in terms of temperature. The figure shows that internal energy solver provides local temperatures about 10 to 20 Celsius cooler than to the total energy solver. For the source modeling part, Lucioni company gave an estimation of the thermal loads that have been uniformly imposed on the affected regions. So, in particular, on bearings, magnets, copper, rotor, and the stator, which is divided in two different regions, the stator yoke and the stator tip, as shown in the figure. Let me spend a few words on the model convergence aspect, because this is very important in this type of application. It is possible to calculate the thermal power exchanged by different boundaries, regions, and streams. And we can say that the steady state is reached when the imposed thermal power in the source modeling is equal to the thermal power exchanged by the air, water, and wood. In the end, one steady-state simulation of this electric motor needs 4 days on 40 cores after 60,000 iterations. Moreover, the setup used for CFL number is listed here for reference. So, using the setup shown above, results in a predictive model, and as can be seen from the comparison between experimental data and numerical results. First, numerical temperatures relating to the bearings differ considerably compared to the experimental one. And basically, this is due to the modeling approach used for bearings. As I said before, in the model, they are modeled as unique cylindrical surface without sphere and lubricant, which facilitate the heat exchange. Apart from that, so apart from bearings, the rotor and the stator temperatures can be considered reasonable, considering also the uncertainty on thermal loads and experimental data. Now, it is important to focus the attention of the predicted velocity in the air gap as a function of the grid resolution. The airflow velocity obtained simulating the complete motor is around 25-30 meters per second, as is possible to see in the left-hand side of the slide. It is calculated with 4 cells in the air gap. This value deviates quite a bit from the theoretical peripheral velocity calculated by the equation in the center part of the slide. Moreover, carrying out a detailed simulation of the air gap with 17 cells, we obtain a maximum air gap velocity of 52 meters per second. That is a value very close to the theoretical one. So, in the entire motor simulation, the non-correct estimation of the velocity in the air gap leads to an underestimation of friction losses that should be corrected, in particular for high-speed regime, as shown in the figure. The correction procedure that we have assumed is based on the detailed simulation of the air gap, which produces a difference in the friction losses compared to the simulation of the entire motor. This friction losses difference then is applied as heat source on the rotor, and in that way the model is able to predict the right temperature distribution. Here are some results from the video on the right-hand side. It is possible to analyze the temperature distribution. On the outlet part is hotter than on the inlet. The stator on the other end has no particular hot spots, while the rotor is heating up toward the exit. Furthermore, as the motor velocity increases, corresponding to an increase in thermal loads, there is also an increase in temperatures throughout the motor. On the other side, the flow field is shown. We are mainly interested in the behavior of the flow velocity in the air gap. And it can be noted that the air slows down from the inlet conveyor and the recirculation zones are created close to walls. The airflow then accelerates in the air gap due to an abrupt decrease in the section. The water cooling system in the central part of the slide heats up to about 6 Celsius for the case with higher thermal loads as confirmed by experiments. Now, since the CFD model is robust and predictive, it is therefore possible to calculate all the results of interest, such as, for example, the role of the air, liquid, and external walls in the heat transfer. And moreover, it is possible to use this model as a development tool, exploring, for example, potential improvement solutions, such as exploring different flow rates or investigating the effect of geometric variations. To summarize, we can affirm that CONVERGE made possible achieving that results thanks to the CHT modeling, the supercycling modeling, the energy solver approach for the total energy, the source modeling, and the contact resistance between components. Finally, CONVERGE permits to evaluate some results such as temperature field, flow field, the role of the air, liquid, and external walls in thermal exchange, the flow rate in the air gap, and the effect of potential geometric variation. So we are now at the end of the presentation. We would like to thank CONVERGE Science for the opportunity to present our activity at this webinar and for the support. Lastly, a special thanks also to our supervisor, Prof. Michele Battistoni. Thank you for your attention.
Thank you so much, Tamara and Jacopo. We really appreciate your presentation and your insight.